Monstrous hurricanes tearing through coastal cities with unforgiving force.
Relentless droughts turning once fertile agricultural valleys into cracked, lifeless dust bowls.
Catastrophic floods submerging entire communities and washing away human infrastructure in a matter of hours. Blistering heat waves pushing the absolute limits of biological endurance and baking the soil beneath our feet.
At first glance, these violent and extreme weather disasters seem completely disconnected. They appear as random, chaotic acts of nature, isolated tantrums thrown by a highly unpredictable atmosphere.
A torrential monsoon failing to arrive in Southeast Asia seems to have no physical connection to a raging wildfire consuming the dry forests of the Pacific Northwest.
But what if these global catastrophes actually share a single unified origin point? What if the invisible strings controlling these disasters are all being pulled from thousands of kilometers away, deep within the dark waters of a single ocean?
The Pacific Ocean is so incomprehensibly massive and so fundamentally powerful that it quietly dictates weather patterns across the entire planet. It acts as a planetary-scale thermal battery, moving unfathomable amounts of heat across the Earth like a giant, invisible thermodynamic engine.
It shapes the genesis of massive storms, dictates the trajectory of seasonal rainfall, drives the flow of deep ocean currents, and commands the stability of entire continental climate systems. And sometimes, even a remarkably small temperature shift inside the remote equatorial waters of this ocean can violently reorganize weather behavior across the entire globe, altering the lives of billions in a matter of weeks.
Hi Questers, welcome to Questhut.
Today, we are diving deep into one of the largest, most complex fluid dynamic systems in the known universe to explore exactly how the Pacific Ocean became the hidden, beating engine behind our planet's climate.
To truly understand why the Pacific Ocean matters so much, we first need to take a step back and examine the fundamental physics of how Earth operates as a rocky planet floating in space.
Our planet is a spinning sphere, constantly bombarded by raw incoming solar radiation from the sun. But because Earth is curved, the sun does not heat our planet evenly. Near the equator, direct sunlight strikes the planet's surface at a perpendicular angle. This delivers highly concentrated amounts of thermal energy straight into the tropics.
However, as you move toward the poles, that exact same amount of incoming solar energy is forced to spread out over a vastly larger surface area. Furthermore, it must travel through a thicker slice of the atmosphere, which scatters much of the energy before it ever reaches the ice.
This unyielding geometric reality creates a massive, permanent, and highly volatile energy imbalance across the globe.
The tropical regions are constantly gaining excess thermal energy, essentially cooking under the relentless solar bombardment. Meanwhile, the polar regions are in a permanent state of severe energy deficit, losing more heat to the dark void of space than they receive.
The laws of thermodynamics dictate that nature will relentlessly seek equilibrium. Earth must find a way to redistribute this massive buildup of heat away from the equator and push it outward toward the poles.
Without this continuous planetary-scale redistribution system, equatorial regions would quickly become unimaginably hotter, boiling away complex life, while polar regions would plunge deeper into hostile, frozen darkness.
Two giant, chaotic, and deeply interconnected fluid systems make this delicate balancing act possible: the swirling atmospheric gases of the sky and the flowing liquid waters of the oceans.
Together, they function as a synchronized planetary-scale cooling machine. And among all of Earth's ocean basins, one dominates this global thermal exchange far more than any other: the Pacific Ocean. The Pacific is the undisputed giant of our world. It is the largest single physical feature on Earth, covering significantly more surface area than all of the continents and solid landmasses combined. It stretches across nearly 1/3 of the entire planet. But the true power of the Pacific lies not just in its size, but in the fundamental physics of water itself. Liquid water possesses an incredibly high specific heat capacity. This molecular structure means that water can absorb, hold, and transport vast amounts of thermal kinetic energy without significantly raising its own temperature.
Because of this unique physical property, the Pacific Ocean essentially acts like a gigantic, slow-moving thermal battery for the planet. It is an inexhaustible reservoir of climate energy, and because its surface area is so immense, a tiny temperature fluctuation of just 1 or 2 degrees Celsius across the equatorial Pacific can unleash enough latent energy to radically alter jet streams on the exact opposite side of the world. The Pacific Ocean does not casually experience the weather, it actively engineers global weather itself. To see this massive climate engine in action, we must look at the continuous exchange of energy between the surface of the Pacific Ocean and the atmosphere above it. Under normal conditions, a massive atmospheric circulation loop known as the Walker circulation completely dominates the tropical Pacific. Powerful, relentless trade winds constantly blow from east to west across the ocean's surface. These winds act like an invisible snowplow, constantly pushing thousands of miles of sun-baked, incredibly warm surface water away from the coast of South America, shoving it toward Indonesia and Australia. As this warm water piles up in the western Pacific, it creates a massive, superheated zone known as the Western Pacific Warm Pool. This immense reservoir of heat radiates powerfully upward, aggressively warming the air immediately above it. That warm, moisture-laden air rapidly rises high into the atmosphere, creating towering thunderstorm clouds, heavy tropical rainfall, and the lush, intensely green climates characteristic of Southeast Asia. Meanwhile, thousands of miles away on the eastern side of the Pacific, near the coast of Peru, something entirely different happens. Because the trade winds have pushed all the warm surface water away to the west, cold, incredibly nutrient-dense water is violently pulled up from the deep, dark abyss of the ocean to replace it. This process is known as upwelling. This freezing deep-sea water chills the air above it, completely preventing the formation of rain clouds, which creates the bone-dry, utterly arid deserts of coastal South America. But more importantly, this upwelling brings centuries-old deep-sea nutrients directly to the sunlit surface. This sparks explosive blooms of phytoplankton, supporting millions of fish and seabirds, creating one of the most incredibly diverse fisheries on the planet. This beautifully balanced system behaves exactly like a living, breathing planetary machine, a giant engine constantly moving heat, moisture, wind, and complex biological life around the Earth. But sometimes, for reasons scientists are still working endlessly to fully predict, this mighty climate engine stutters. It breaks its normal rhythm. The powerful trade winds that normally push the warm water to the west suddenly weaken. Sometimes they collapse completely. Without the sheer force of the wind physically holding it back, that massive, elevated dome of warm water piled up in the western Pacific inevitably collapses. Driven by gravity, this immense pool of heat begins to slide backward, surging eastward across the vast ocean, traveling deep underwater as a massive surge of energy known as a Kelvin wave. Months later, as this immense dome of superheated water finally crashes into the coast of South America, ocean temperatures in the eastern Pacific violently skyrocket. The vital, nutrient-rich upwelling completely shuts off. And suddenly, the normal weather patterns across the entire Earth begin changing with it. This incredibly powerful and disruptive phenomenon is known universally as El Niño, and its extreme opposite phase, where the trade winds become hypercharged and equatorial ocean temperatures violently plummet, is called La Niña. These are not just isolated ocean anomalies, they are massive, planetary-scale climate reorganizations. Because when Pacific Ocean temperatures physically shift, the Earth's entire atmosphere is forced to mathematically react to the new distribution of thermodynamic energy. The massive rain band that usually hovers over Indonesia is dragged thousands of miles eastward toward the central Pacific. High-altitude jet streams are violently pushed off their normal latitudinal tracks. seasonal, life-giving rainfall zones migrate entirely across different continents.
A slight warming of just 2 or 3 degrees in one specific region of the Pacific Ocean can trigger crippling, multi-year droughts in the dense Amazon rainforest and the sprawling outback of Australia.
At the exact same time, that exact same thermal shift can cause catastrophic, unrelenting flooding and deadly mudslides in California, Peru, and East Africa. This is how deeply, beautifully, and terrifyingly connected Earth's entire climate system truly is.
During historically intense El Niño events, the cascade of global consequences is absolutely staggering. Entire countries that rely on seasonal monsoons for survival experience catastrophic agricultural failures.
Other regions that are historically arid suddenly receive years' worth of extreme torrential rainfall in a matter of days, completely overwhelming human engineering.
The Atlantic hurricane season is often heavily suppressed by intense upper-level winds, while simultaneously, the Pacific typhoon season becomes monstrously amplified, spawning record-breaking superstorms.
The damage is deeply biological too. Without the nutrient-rich upwelling off the coast of the Americas, the foundational phytoplankton rapidly die off. The entire marine food web completely starves from the bottom up.
Across the globe, sensitive, ancient coral reefs, utterly unable to biologically handle the sudden spike in ocean temperatures, violently expel their symbiotic algae, leading to massive, ghostly white coral bleaching events.
During a strong El Niño, the raw heat released by the Pacific is so massive that the global average temperature of the entire planet visibly spikes on meteorological charts.
Earth's atmosphere behaves far less like a collection of separate regional weather systems and much more like one giant, heavily interconnected fluid dynamically wrapped around a spinning rock.
The climate of planet Earth is not local. It never has been. It is entirely planetary.
And this stunning realization brings us directly to one of the most critical and alarming discoveries in modern climate science.
Over the last century, as human civilization has rapidly pumped billions of tons of carbon dioxide directly into the atmosphere, we have exponentially thickened the invisible blanket of greenhouse gases surrounding the Earth. But the atmosphere itself has only absorbed a very tiny fraction of that trapped excess heat.
The vast, dark, immensely deep oceans have absorbed more than 90% of the excess thermal energy, completely trapped by humanity's greenhouse gases. Not the air we breathe, the oceans. This completely redefines our understanding of the planet. It means the oceans are absolutely not just passive background features. They are the primary, active, heavy regulators of planetary climate equilibrium. The atmosphere is highly volatile, responding quickly to surface changes. But the deep oceans are the massive, controlling force driving the long-term movement and storage of heat across the world. In many mechanical ways, the atmosphere is merely the steering wheel of the global climate. But the deep, churning oceans are the unstoppable, roaring engine. Today, marine scientists are continuously observing unprecedented ocean temperatures simultaneously spiking across the entire planet. The global ocean is running a continuous, dangerous fever. Massive patches of superheated water, known as marine heatwaves, are becoming increasingly common, lasting far longer and striking with much greater intensity. And from a purely raw thermodynamic standpoint, warmer oceans fundamentally mean that drastically more raw, combustible energy becomes continuously available to fuel extreme weather systems. Hotter surface water drives much more rapid evaporation into the sky. More suspended moisture in the atmosphere directly leads to much heavier, highly concentrated, and catastrophic rainfall events. More thermal energy feeding into tropical depressions drives the rapid intensification of stronger, immensely more destructive cyclonic storms. Ultimately, it points to a state of far greater, highly unpredictable climate instability. Human civilization is effectively pouring raw energetic fuel straight into the Earth's delicate climate engine. And because the mighty Pacific Ocean is such a dominant, overwhelmingly massive part of that thermodynamic engine, Any permanent structural changes happening deep within its waters will inevitably and violently ripple out across the entire globe. The Pacific Ocean is quite literally one of the greatest, most intricate energy transfer systems currently operating in the known solar system. It is a planetary-scale thermodynamic engine, quietly redistributing immense heat, shaping the genesis of deadly storms, commanding the survival of global ecosystems, and doing the absolute heavy lifting to help stabilize the fragile climate of an entire world. As humanity relentlessly continues warming the planet, truly understanding the deep, hidden mechanics of the oceans may quickly become the single most vital scientific challenge of our time. Because whether we fully realize it or not, the future survival and stability of human civilization may heavily depend not only on what happens in the volatile, stormy skies high above us, but also on the silent, rapidly shifting, and deeply powerful currents hiding within the dark oceans below. What do you think? Could rapidly changing ocean dynamics, failing currents, and extreme marine heat waves become the ultimate, most incredibly difficult climate challenge humanity faces in the critical decades to come? Will our current human technology and infrastructure be able to successfully adapt to a dangerously overheated Pacific engine? Comment your thoughts below. And if you enjoyed this massive, comprehensive deep dive into the hidden thermodynamics of Earth's climate engine, subscribe to Questhut. Keep asking incredibly difficult questions daily. Keep boldly exploring the awe-inspiring systems that shape our universe, and I will definitely see you soon.